Hi students, in the last classes we were discussing about the distinguishable particles like our classical particles, where you can make use of the distribution function Maxwell-Boltzmann distribution function, that is f empty of epsilon, and you got the expression a e raised to minus epsilon by dt. Okay, and by using this we find out n of epsilon d epsilon is equal to g of epsilon f of epsilon d epsilon, and we got the expression, and we got the average molecular energy, average speed distribution, and all those things for an ideal gas. Ideal gas is an example for a particle which obey the Maxwell-Boltzmann distribution function. Okay. Now, what you need in the first class, we classified the particles into three. One is the particle they are distinguishable. Second one, particle they are indistinguishable but they are bosons. And the third one is particle they are indistinguishable but they are fermions. That means you can categorize the total particles into three. Out of this one we have discussed, and the distinguishable particles they obey Maxwell-Boltzmann distribution function is one. Okay. Now we will go to the particles they are called the indistinguishable particles. The indistinguishable particle, we have two categories. That is the particle which obey Pauli's exclusion principle and particle which do not obey the Pauli's exclusion principle. But in both the cases I already mentioned what is their importance. They are indistinguishable, or their wave functions overlap appreciably. So you cannot distinguish one from another. Okay. So these studies are coming under quantum statistics. Quantum statistics. This you have to discuss the quantum statistics. So this quantum statistics, this is for fermions and for bosons. Both are indistinguishable particles. Or you can say the wave function psi overlap. Wave function psi overlaps. Okay, and these fermions they have odd half integral spin, and these fermions have integral spin. That is, here it comes half, 3 by 2, 5 by 2, 7 by 2, like that, but here it is 0, 1, 2, like that. Okay. So these are the two particles, and we have to discuss about this. The first thing what coming in our mind is, since these particles are indistinguishable and wave functions overlap, even though you can count it, you can count the fermions and all. Okay. So if you take a system as a whole, then the wave functions for let us take around n particles or small n number of particles. Then the total wave function for this system, the particles in the system, you can write it as psi of 1, 2, 3, etc., n. And this you can write it as this is multiplication of the wave functions of individual particles. So psi of 1 into psi of 2 into psi of 3, and the wave function of the first particle, wave function of second particle, wave function of third particle, etc. Right up to psi. I don't know whether this is visible in the camera. Yeah, like this. Okay. Now, this is a situation. So that what you have done, you have small n number of non-interacting particles. So the total wave function of this n non-interacting particles, you can write it as the multiplication of, or the product of all the wave functions of this individual particles. Okay, so that I have written. Let us instead of taking n number of particles, let us take two identical particles. That is, you have a particle 1 at a particular state A and a particle 2 at a particular state B. Then what is the situation that we want to look at it? So we are considering two identical non-interacting particles. So you have a wave function psi 1 at a particular state A. The state A, and psi 2 at a state B, or vice versa. So I am just indicating it as psi A and the particle 1 at a quantum state A and particle 2 at a quantum state B. So the important thing what you have to take in mind is that since these particles are indistinguishable particles, even if you change the particle, or even if you exchange the particle with different quantum states, that means if you are exchanging, that is a particle 2 you are taking at a quantum state A and particle 1 at a quantum state B, then the thing is the probability density that you cannot distinguish, or it won't change. Okay, actually I went for a small work. Now what we want to discuss, if you exchange the particle between these quantum states, the probability density, that means psi square, remains the same. This remains the same because you cannot because these are the indistinguishable particles. So if the particles are exchanged, then this remains same for the system. Okay. Now what you have to look at it, you have two particles, so that is two identical particles at two different quantum states. Now this tells you psi square of 1 comma 2 is equal to mod psi square of 2 comma 1. So this is a mean. So even if you change the particle or exchange the particle between these two quantum states, quantum state A and quantum state B, the probability psi square, mod psi square remains the same. Okay, so we will just write it like this way, and if you take the solution of it, that is psi of 1 comma 2, that will give you plus or minus psi of 2 comma 1. Okay, so you have two situations where one situation is if you exchange the particle by 1 and 2, you are getting positive psi of 2 comma 1. So it doesn't make any difference in the wave function. And another is psi of 1 comma 2 is equal to minus psi of 2 comma 1. So that means here the sign, it is changing the sign of the wave function. Okay, so I will repeat one more time. We have indistinguishable particles. I am taking two identical particles at two different quantum states, quantum state A and quantum state B. So I am taking the particle 1 at a quantum state A and particle B at a quantum state 2. Okay. Now what I am doing, since these particles are indistinguishable, so you cannot distinguish each other. So if you take the probability, that means probability is psi mod psi square. If you exchange the particle between these quantum states, this remains the same. Okay. So that I wrote. That means mod psi square of the particle 1 at A and particle 2 at B is equal to mod psi square of particle 2 at A and particle 1 at B. This is a situation. Now what you are going to take, because this square is equal to this square, so when you take the solution you will get psi of 1 2 is equal to plus or minus psi of 2 1. That you know in this general case. And now what it indicates? It indicates two situations. One situation, if you exchange the particle, your wave function remains the same. The second situation is, if you exchange the particle, the wave functions take a negative sign. So this kind of particles, or this situation we call it as a symmetric. So the wave function is symmetric. And here the wave function is what is called asymmetric or anti-symmetric. Anti-symmetric, because it possesses symmetry. Even if you exchange the particle, you are getting the same. But here it doesn't possess a symmetry, or it is anti-symmetric. That is what you are getting a negative sign in the second situation. So one thing is clear here. You have two kind of wave functions. One is the symmetric wave function and anti-symmetric wave function. That means the wave function which are not affected by the exchange of particles, that we call it as symmetric, and the wave function which are affected by the exchange of particles, that we call it as anti-symmetric. Now I am taking, can you see this? Let me rotate a little bit. Yeah. Now I am calling psi 1 is equal to this is a psi 1 is equal to your particle 1 at quantum state A and particle 2 at quantum state B. So this I am calling it as psi 1. Okay, the total wave function is psi 1 in this situation. Second situation I am calling psi 2 is equal to my wave function 2 at a quantum state A and wave function particle 2 at quantum state A and particle 1 at quantum state B, and this I am calling it as psi 2. So this is I am just giving this nomenclature like this. Now, what is important thing we have to keep in mind is that since your particles are indistinguishable, so we cannot say which one is at quantum state A and which one is at quantum state B. So we have to make the wave function in such a way that you have to keep both the combination of both of it. Okay, that we want to do. Okay, so we will just do it. Let me rotate. So here we need the combination of these two things. So this combination actually making the probability of equal likelihood of these two states, that is the particles at particle 1 at quantum state A and particle 2 at quantum state B, and the second is particle 2 at quantum state A and particle 1 at quantum state B. Okay. Now we have, I told within the indistinguishable particles you have fermions and bosons. So first we will take the fermions. The fermions, I told it is they are odd half integral spin particles. The fermions are odd half integral spin particles, and these particles, they are described by, these fermions are described by asymmetrical and symmetric wave function. So that means on exchange of your particles you must get a negative sign. So this I am not going to derive it in detail, so I will just go to it. How to represent this anti-symmetric wave function by using the combination of these two wave functions. Okay, so I am calling it as psi f, that is a wave function for the fermions. So this we write it like this: 1 by root 2. Actually, this is a normalization constant. Then psi A, that is the particle 1 at quantum state A, into psi B at 2, that is particle 2 at quantum state B, minus psi A, the particle 2 at quantum state A, into particle 1 at quantum state B. So this will give you the wave function for fermions, and this wave function is an anti-symmetric wave function. We can check it out easily. How? You just exchange the particles. That means instead of this, the particle at the quantum state A, I am just exchanging with the particle 2 at the quantum state A. And particles at the quantum state B, it is I am taking it as particle 1 at the quantum state B. So how do we get it? If I exchange, that means this is psi of 1 2 like that. Then this term give you the, okay, let me do it. So this 1 2. Now psi f of 2 comma 1, that means I just flip the particles from the quantum state. So what will be here? 1 by root 2 psi A of 2 psi B of 1 minus psi A of 1 psi B of 2. That means you know the nomenclature. What does it mean? So now look at this expression and this expression. If you just multiply with a minus 1, what you will get? This will be equal to this one. So you are getting psi f at 1, 2 is equal to minus psi f at 2, 1. So this is a anti-symmetric wave function. So for the fermions, this is the anti-symmetric wave functions. Okay. Now we will go to the second particle. What is the second particle we talked? That was the bosons. So the bosons, they have integral spins and they are described by symmetric wave functions. So I will just do it here. Yeah, I will do it here. Then you can just rotate it a little bit. So for the bosons, the wave function is represented by psi b. That is equal to, can you, I hope you can see it. Yes, you can see it here. 1 by root 2 psi a1, that is particle 1 at constant A psi 2b plus psi 2 A into psi 1b. So this is a symmetric wave function. Okay. So this is the two things very important. Whenever you do, you deal with the fermions and bosons, you have to choose the appropriate wave function, because for the fermions you have anti-symmetric wave function and for the bosons you have a symmetric wave functions. Now what you need to know, you have the wave function for bosons and wave function for fermions. Then what would be the likelihood to stay both the particles in a particular state A? Okay, I am taking both the particles in a quantum state A. What is the probability for that, or likelihood to stay both the particles in the same quantum state? So I am just taking my wave function as psi m. That means both the particles are in the same quantum state. So I am just writing it as psi m. What is psi m? Psi m means your particle 1, it is at a quantum state A, and particle 2, that also in a quantum state A. Both are in the same quantum state. Now we will check what is the likelihood to possess both the particles in the same quantum state for the fermions and also for the bosons. Okay, so that we will get an interesting result out of it. So first we will write the wave function for bosons. What was it? Psi b is equal to 1 by root 2 psi A with the particle 1, and again psi A with particle 2, because both the particles are in the same quantum state, plus psi A with the particle 1, sorry, particle 2, and there is psi A with the particle 1, isn't it? This is the situation. Now both are equal, so you can write it, or this is nothing but the psi m. I am just calling it as psi m, and this also psi m. So you can write this is equal to 1 by root 2 times psi m. Okay, so you are getting what is called 2 and 2 will go, so we will get root 2 psi m. Now we are looking at the probability. You need the probability density. Probability density means psi square, mod psi. So what is that? Mod psi square. So mod psi square, I will just rotate it a little keep it. Yeah. Mod psi b square. What is that? Mod psi b square is psi b star psi b. Actually, basically this is the thing. So what is psi b? Here you have a square root of root 2 psi m. So this is equal to psi b star is root 2 psi m star, and psi b is again root 2 psi m. So this is root into root 2 psi m. Okay, just keep it. Now we will look for the fermions. Let me rotate it a little bit. Yeah, okay. I will just write it here itself, because here you need only two things. One is this become minus, because the rest of the things is same. Because you have only one quantum state A, and both the particles are located, or you are looking the probability for the both the particles locating or sitting at the same quantum state. So here 1 at A, 2 at A, again 2 at A, 1 at A. So what would be this? This is equal to, so this is equal to 0. So this is very interesting thing. So here what you got, because for the bosons, the probability or the likelihood to stay both the particles in the same quantum state is twice the probability of a distinguishable particle. You are getting twice. But in the case of fermions, it is totally 0. That means you cannot occupy two particles at the same quantum state. So this is nothing but our Pauli's exclusion principle, or the statement of the Pauli's exclusion principle that you got very easily from the approach. Okay, so this is very interesting thing. So this results you can make it more general. That is, in a system of bosons, the presence of a particle in a certain quantum state increases the probability that other particles are to be found in the same state. And from the second result, what you are getting, the presence of, or in a system of fermions, the presence of a particle in a certain state prevents any other particle from being sitting at the same state. So this is the Pauli's exclusion principle, and for the bosons, actually it increases the probability. Okay. So this I am just stopping this video here. So now we will go to this Bose-Einstein distribution function and Fermi-Dirac distribution function in detail. Okay. So first you have to understand the fermions have, or they possess, antisymmetric wave functions, and the bosons possess symmetric wave function. That's it. And the remaining things about the distribution function that we will discuss.